everyone. Welcome back to Learning at 11th Hour. Today we are going to look at three distinct problems, two of which would be solved using node analysis method and one would be solved using the mesh analysis or the loop current method. So let's start with the problem. The first problem looks like this. So here we need to compute the node voltages VA, VB and VC. So how do we do that? Let us begin by marking the node currents first. So for node A, we are going to consider that from every node, all the currents are going to be moving out, except if there is a current source connected to it. We are not going to disturb the direction of current coming from a current source. So for node A, there is a 3 amps connected to it, which is entering node A. The rest of the currents, let us assume that they are moving out. So this is one current and this is another current. Now, we know that for a resistor which is connected across terminal X and Y with a resistance of R, the current moving from terminal X to Y, the value of I is going to be nothing but minus of Vx minus Vy by R, which means that the current is moving out of the node X and the node X is at a higher potential compared to node Y. So Vx minus V by Vy divided by the resistance R. So therefore the negative sign here represents that the current is moving out of this particular node. So following this convention, let's frame the KCL at node 1. So here what we are going to get is we are going to get VA minus VC by 7. This should be preceded by a minus sign because the current is moving out of node A, followed by minus of VA minus VB by 2, followed by the 3 amps which is entering. So plus 3. This is equal to 0. This is my first KCL equation or first node voltage equation. The second one is going to be applied at node B. So KCL at the second node. So if instead of 1, let me call it as A. So this is node B. At node B, let us now consider that the currents are going to be moving out. So one like that, and the other one like that. So these are the three currents. Let's write the KCL equation now in terms of the node voltage VB. So minus of VB minus VA by 2 minus of VB minus, there is a 3 volts voltage source over here. So VB minus 3 by 2 and minus of VB minus VC by 3 is equal to 0. So this is my second equation. The third one, applying KCL at node C. So what we get is, let's mark the currents. So this is going out like that from the node C. So all the three currents are moving out and the equations would be minus of VC minus VA by 7 minus VC by 1 because D is supposed to be the reference node over here whose value is 0 volts. So I could have written VC minus VD by 1, but VD is equal to 0. So that boils down to VC by 1 and minus of VC minus VB by 3. This is equal to 0. This is my third equation. So having framed the three equations, we can now solve the three equations to obtain the values of VA, VB and VC respectively. We can now simplify the three equations which we just obtained and finally the three equations would appear like this. And on solving the three equations, we can get the value of VA as 9 volts, VB as 5 volts and VC as 2 volts. So this can be solved using the calculator. We can have three simultaneous equations solved at the same time, or we can go for the matrix method. Using the Cramer's rule also, we can solve this system of equations. So in this way, we have applied the node voltage method to obtain the node voltages VA, VB and VC. Moving on to the next problem. This problem involves dependent sources. So we have both current dependent current source and voltage dependent voltage source in this problem. But all they want us to do is compute the value of Vx, and we need to use the node analysis in doing so. So if we look at this circuit, here we see that there are several dots that are available here, but they are all one and the same node, because if we see, there are no elements connected in these wires. So therefore all of these uh, are actually one and the same node, so I can call it as node n1. This is n2, because between this point and this point there is an element that is connected, or we can say that at this node this element and this element are meeting. So therefore these two are the two nodes that are available right now. So if we want to apply KCL, we can do that simply. Here we can go for the nodal analysis. So this would be V1 and this would be the node voltage V2 for the nodes 1 and 2. In order to obtain the nodal equation for node 1, we are going to apply KCL at node 1. So when we do so, we see that the 6 amps is entering the node. So we'll say plus zero point 0.6, zero point 0.6 amps. And IY is leaving this particular node. So I'll call it as minus IY. And 25 IY is entering the node. So plus 25 IY. And again, V1 by 50. That is going to be the current that is coming out of this node. So minus V1 by 50. So all this, and then we have this current minus of V1 minus V2 by 40. So this is equal to 0. Now, in this entire equation, we can actually replace the value of Iy and V1 and V2, in the sense that V2 is nothing but zero point 0.2 Vx, because it is after all the voltage between this node and the reference. So the drop across node 2 and the reference node is nothing but zero point 0.2 Vx. So therefore we can say that V2 is equal to 0.2 Vx. So this is the first constraint which we can deduce from this circuit. The second one is the drop across the nodes 1 and the reference node is nothing but Vx. So therefore, we can actually say V1 is nothing but Vx. So that becomes our second constraint. The third constraint is, if we see that this resistor, 100 ohms resistor, is connected in parallel to this node 1 and the reference node. So all these branches are actually parallel to each other. So therefore, we can say that the voltage drop across this node is also Vx, which means that by applying Ohm's law, we can say that Vx is equal to 100 into Iy, or Iy is equal to Vx by 100. So these are the three constraints which we have obtained. We can now replace these values in this equation. So what do we get? Zero point 0.6 minus of Vx by 100 plus 25 Vx by 100 minus Vx by 50 minus Vx minus zero point 0.2 Vx by 40 is equal to 0. So this equation is now just having one unknown, which is Vx. And therefore, if we solve this equation for Vx, the value of Vx can be obtained as minus 3 volts. So this is how we go for nodal analysis. We should ensure that we are marking or identifying the nodes correctly, after which we can assume that the currents associated with that particular node are assumed to be coming out of the node, and then we can frame the KCL equations for that particular node. So that's all with today's video. Hope this video was useful to you all. In the next video, we'll be discussing about super node concept and how we can solve complex circuits by applying the concept of super node. Thanks for watching. Please do subscribe to my channel for more such videos on circuit theory.